Questions? No questions? Okay, so we finished section 5. Today we're going to do section 6, and as I said on Friday, on Wednesday we have a quiz from chapter 1. So that's the game plan. It's going to be at the beginning of the class, and it's going to be I think probably about half an hour long. Okay, so let's see. We started talking about continuity and we started talking about limits, and so today we're actually going to go back to limits and actually talk a little more about those limits that do not exist. So for example, the topic of the day is more or less infinite limits. So the idea is the following. Remember when we looked at the limit as x goes to 0 of 1 over x squared, what did we say about this particular limit? Well, since it's 1 divided by 0, you can't divide by 0, and so the claim was that this limit does not exist, right? We're not saying from this, in this section we're not going to say that this limit in fact exists, but we're actually going to be a little more specific about what do we know about this particular limit. And so the idea is rather simple. If I'm to actually make a table of x and 1 over x squared, okay? Notice first of all that I'm looking at 1 over x squared, which is an even function, which basically means that it doesn't matter if I look at the plus or the minus side, it'll still be the same thing. So the idea is, what happens if you actually make x smaller and smaller? So, and it should be relatively easy to follow this. So, if x is 0.1, what's 1 over x squared? 100, you say? It's 1 over 0.01. Right? Do you want me to write it as a fraction? Will you see it a little better that way? Keep in mind, 0.1 is 1 over 10. You square that, and you reverse it, since it's 1 over that, right? 10 squared is 100. 1 over 100, or 1 over 1 over 100 is 100. Does that make sense? Okay. How about 0.01? 10,000, you say? Again, 0.01 is 1 over 100. You square 100, you end up with 10,000. Long weekend? 0.001. What do we get? What do we call this? A million? Lots of zeros? So this, why? Because this is 1 over 1,000, right? You seem to have awful difficulties with decimal points. Is this making sense? Yes. Alright, so then if this is the situation, then what would you expect that limit to be? Well, notice that, and by the way, I'm just looking at this, but I could actually easily have plus or minus, plus or minus, plus or minus. It wouldn't change anything, right? Because we're looking at the square, right? So what happens? As x gets smaller and smaller, the value of the function gets larger and larger, right? Eventually it'll surpass the national deficit. But the point is, the limit is in fact infinity. Does this make sense? Now again, the key idea is that infinity is not an actual number, right? And so this doesn't mean that the limit actually exists. We're basically just saying, we're denoting the fact that as x gets to 0, this limit gets larger and larger. That's basically what we're saying. We're saying that it basically grows as much as it possibly can. Does that make sense? Yeah? Well, it shouldn't surprise us because remember the graph of 1 over x squared. Right? As x gets closer and closer to the origin, your graph shoots up. Does that make sense? Yeah? Wonderful. So why don't we make this a definition? The notation, the limit as x goes to a of f of x is equal to plus infinity, means that the values of f of x can be made arbitrarily large by taking x to be sufficiently close to a. And we've seen this before, but not equal to a. To a. X is sufficiently close to x at all times, since it's exactly the same. And this is one of the reasons, bless you, this is one of the reasons why we actually can, in fact, say that that limit is infinity, because the idea is you can't actually divide by 0, but we are not actually dividing by 0, right? Because the whole point is we're never actually equaling to 0. We're just getting closer and closer to it. Does that make sense? Okay. So similarly, it'll work the same way if I look at a situation in which I guess minus infinity. So we'll look at one example, one particular example. What is the limit as x goes to 0 minus of 1 over x? Well, since you're so good at decimal points before, let's see if your skills have improved. So x and 1 over x. Minus 0.1. What's 1 over x? Negative 10? How about minus 0.01? Negative 100. Minus 0.001. Negative 1,000. Oh my god, you're so much better now. That's because it's not squared, right? Does this make sense? So what is the limit? Negative infinity. Everybody sees how this works? The idea is if you look at the table, as you get closer and closer to 0 from the left, your values get a lot more negative, if you so choose to say. I'm usually trying to stay away from a statement of they get very small, because usually when we say small, we're kind of thinking about being close to 0, right? That's why I kind of tried to stay away from small, and I said they get very negative, which is not really a correct mathematical way of saying things, but anyway, is this making sense? Okay, so what is the limit as x goes to 0 plus of 1 over x? Positive infinity, right? So then what can we say about the limit as x goes to 0 of 1 over x? We say it does not exist, right? And this is the difference versus what we had before. Coming from both directions, even though none of these actually exist, the fact is one of them goes to plus infinity, the other one goes to minus infinity, so I can't combine the two and say they go to, some sort of an infinity, because they go in different directions. Does that make sense? Well, you have witnessed The birth of vertical asymptotes. Definition. The line x is equal to a is called a vertical asymptote of the curve y equals f of x if at least one of the following statements are true. At least one of the following statements are true. The limit as x goes to a of f of x is equal to plus infinity. You know what? I'm going to combine them. Actually, no, that's fine. I'll just write them all out. Well, I don't want to necessarily confuse you more. So if the limit as x goes to a of f of x is either plus or minus infinity, if the limit as x goes to a minus of f of x is equal to plus or minus infinity, and the limit as x goes to a plus of f of x is again equal to plus or minus infinity. So as a general rule, if either of these holds, then we're in business. Now, the one thing I should point out is if the first one holds, then both of these will hold anyway. Right? Does that make sense? But you could have a combination of them. So, any questions about this? Yes.
Is it supposed to be a minus for both of them? On the
Yes. Oh, a plus for this one. Sorry.
oh.
Yes.
So, whenever you said that you had to limit of x
Oh.
is equal to positive infinity as 6 and the other two, so like the whole top line, that is infinity. And you just need to even have like a negative infinity and plus infinity.
Oh, you can't. See, that's why it says if at least one of them is true. Okay? And clearly if this holds, then this is not going to hold. But if the plus infinity holds, then by definition, going from the left and going from the right is going to be the exact same thing. So that's why it says at least one, because you could actually have just one. Like for instance, you could have this, but none of the other ones. And we can actually have a very good example of this. Can you give me an example in which this would hold, but none of the other ones would? The reason why I'm trying to get to this because in pre-calculus you were taught that, you know, here's this rational function. If the denominator is 0, boom, that's a vertical asymptote, right? Right? Okay. So how about if I look at f of x equals ln of x? Do we remember what the domain of this particular function is? Since he was in your pretest. 0 to plus infinity. You can't have 0 and you can't have negative numbers, right? Do you remember what the graph of this function looks like? It looks like this, right? That would be the graph. If you look on the graph, we notice that the limit as x goes to 0 plus of ln of x ends up being minus infinity. And so you witnessed your first function that is not a rational function, is not a ratio of anything, yet it actually has a vertical asymptote. Everybody sees this? Yeah? Okay. So Maybe I should stop here and do some examples. Let's see exactly what examples are we looking at. No, let's keep going with the definitions over here. So, how about if I look at f of x equals x squared minus 1 divided by x squared plus 1. And I guess I'm cheating because I'm using the problem from the book. What can we say about this particular function as an end behavior? And I'll give you a hint. Graphically speaking, this function looks like this. More or less. In the picture it looks much better. In their picture anyway. This I guess would be minus 1, this would be 1. And we're going to actually learn how to graph these functions a little later on. So we could easily take values, and I don't necessarily want to do this because it's not necessarily that easy to figure out. Well, okay, maybe I'll do it. Since saying it in words doesn't necessarily mean anything. How about if I look at plus or minus 1,000? So the question is, what happens when x gets very, very large, or very, very negatively large? So at one, okay, let me erase one of these zeros since I don't have more than that. So plus or minus 100, you get 0.9998. And if you look at plus or minus 1,000, you're going to look at 0.99998. So what would you guess is the behavior when x reaches infinity? That is, the limit as x goes to infinity of f of x is going to be 1. Does everybody see this? Yeah? Well, we have witnessed a horizontal asymptote, but before that, let's actually give a name to this. Let f be the function defined, or be a function I should say, defined on some interval a to plus infinity. Then the limit as x goes to infinity of f of x is equal to capital L means that the values of f of x can be made as close to L as we like, by taking x sufficiently large. Okay? Alright, we're going to devise tools to actually come up with these limits without actually having to go to a table. Since I'm hoping everybody remembers how much fun the tables were in section 3? Okay, so as I said, we now have the tools to actually call this something. So the line y is equal to capital L is called a horizontal asymptote of the curve y equals f of x if either the limit as x goes to infinity of f of x is equal to capital L, or the limit as x goes to minus infinity of f of x is equal to capital L. Okay, so far so good? Yeah? So let's find out tools to actually come up with these limits. And then we can actually go to some examples and see how things work. So, what would you guess the limit as x goes to infinity of 1 over x to be? Zero. Do you see that it's 0, or should I whip out a table? Again, it has decimals.
We see it.
Okay, so how about x? And 1 over x. X gets large, right? So let's start off at 1,000. Not 0.1000, but 1,000. What is 1 over x? 0.001. How about 100,000? 0.00001. Do you see where I'm going with this? Everybody sees that the limit is 0?
Yes.
Wonderful. How about if I go to minus infinity of 1 over x? Well, does it change anything that I go to minus infinity? Minus, 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 minus. Still goes to 0, right? It just goes from the other direction. Everybody sees that? And so it ends up being 0, right? Yes? Wonderful. So with these lovely tools in hand, well, I guess I should make it a little more of a general statement. In fact, of what we, in lieu of what I just said, what is the limit of x goes to infinity of 1 over x to the n, where n is any number? So how about 1 over x squared, x cubed, x to the 1000, or whatever other situation may be? This is the same thing as the limit as x goes to infinity of 1 over x to the nth power, which is going to be 0 to the nth power, which is 0. Does that make sense? Yeah? Well, I'm going to be lazy here. Plus, minus, plus, minus. Same goes with minus, right? Okay. So now that we have these lovely tools, let's look at a few problems. And we'll come back to... I'll talk a little more about other stuff as we get close to things. So let's see. As far as homework, you have 2, 4, and then all the other limits over there. So that being said, do you want me to do number 1?
Yes.
So much enthusiasm. Okay, let's see if I can actually more or less reproduce this graph. So if this is 1, minus 1, 1, 1, 2, my graph looks like this. It starts over here, goes through 0, goes up there, comes down, and then goes up, and then comes from over here, and okay, more or less. If you don't believe me, go to page 66. Okay, part A. What is the limit as x goes to 2 of f of x? Infinity. Everybody sees that it's infinity? Okay. Part B. What is the limit as x goes to minus 1 minus of f of x? Again, plus infinity. Everybody sees that? No? Why no? 1 minus, minus 1 minus means I'm on this side of the graph. So as I go on the graph, I shoot up. Right? Alright. Part C. The limit as x goes to minus 1 plus of f of x. Negative infinity. Everybody sees that? Okay. Part D says the limit as x goes to infinity of f of x. One. Yes?
Why?
Why? As x goes to infinity means I keep moving this way, right? So I follow the trace of my graph. As x goes to the right, I keep graphing my graph, and based on my picture, yeah, it doesn't look like 1, but the idea is it will keep going on 1, right? As I said, I try to be as accurate as I could. 66 actually will be, by page 66 will actually have the picture a little more accurate. And the last, but not least, the limit as x goes to minus infinity of f of x. It'll be 1 again. Right? Now notice the difference, and this is why they... Okay, well, I guess my graph doesn't portray that. But anyway, the point is, notice the difference between the left and the right. Notice here how it actually is smooth going to 1. Here it looks like it's jagged originally, but it gets closer and closer to 1. And so the idea is it doesn't matter that you keep crossing it. The point is, if it actually gets closer and closer to it as you go to infinity. That's because my graph... Okay. Fine. How's that? Perfect, she says. Is this making sense?
Yes.
Okay, so now looking at this particular graph, how many horizontal asymptotes can you possibly get? 2. Can you ever get more than 2 horizontal asymptotes? The answer is no. Why not? By definition, a horizontal asymptote is defined to be the limit as x goes to either minus infinity or plus infinity is equal to a number, right? Which means there's only 2 choices, minus infinity and plus infinity. Does that make sense? Which means you have 3 possible choices. No horizontal asymptotes, 1 horizontal asymptote, or 2 horizontal asymptotes. How about vertical asymptotes? How many can you get? As many as you want, right? Can you give me one example of a function that has an infinite number of asymptotes? Tangent. Very good. Everybody understands that? Think about the graph of tangent. It keeps going and going and going, right? It's a periodic function, so it'll keep repeating the same vertical asymptotes, right? Does that make sense? Okay. Notice I didn't ask you to give me an example of a function that has no vertical asymptotes, because I'm guessing that's very boring. Okay. Yes?
It says also the equations of the asymptotes.
Oh, the equations of the asymptotes. Oh, thank you. I skipped that part. The equations of the asymptotes. What are the vertical asymptotes? By the way, that's what I'm going to be denoting vertical asymptotes, and horizontal asymptotes are going to be just HA, a lot less to write. Okay, so what are the vertical asymptotes? So x equals -1, x equals 2, right? How about horizontal asymptotes? Y equals 1, y equals 2. Right? Do you understand why we call these y's and why we call these x's? Everybody understands this? the graph of a vertical line is described by x equals whatever number you have, right? The graph of a horizontal line is described as y equals whatever number, right? Okay. So let's see what else. Sketch the graph of an example of a function f that satisfies all the given conditions. I guess we have 3, 5, 7. I only assign number 4, just so you get a little warmed up with them. Should we do maybe number 5?
Yes.
Okay, let's not do number 5. Bless you. How about we do... Okay, let me just ask you something. The reason why I said let's not do number 5 is because I never actually talked about this. Do you understand what it means to say the limit as x goes to infinity of f of x is equal to plus infinity? Can you give me an example of a function that would actually have that behavior? X squared, x cubed, whatever polynomial you want, as long as it has a positive number in front of it. It says that as x goes to the right, my function keeps going up, right? That's basically the idea. Does that make sense?
Wait, could it be linear too?
It can be any polynomial. Okay, as long as, sorry, I should say it can be any polynomial as long as the leading coefficient is positive. Remember, if the leading coefficient is negative, then you're actually going to end up going down. This was stuff that you actually talked about in pre-calculus. Okay, so number 5 or number 7? I'm only going to do one. 7? Okay. F of 0 is equal to 3. The limit as x goes to 0 minus of f of x is equal to 4. The limit as x goes to 0 plus of f of x is equal to 2. The limit as x goes to minus infinity of f of x is equal to minus infinity. The limit as x goes to 4 minus of f of x is equal to minus infinity. The limit as x goes to 4 plus of f of x is equal to plus infinity. And the limit as x goes to infinity of f of x is equal to 3. Okay? I'll let everyone catch up. Okay, so now let's draw a lovely graph over here. So what do we know? Well, f of 0 is equal to 3, right? So if I put some labels on this lovely graph, I know, here I'll use red or orange, whatever that color is. I know I start there. Then I know that the limit as x goes to 0 minus is 4, 0 plus is 2, right? So that says that at 0 minus I'm at 4. And at 0 minus I'm at 2. And now what else do I know? Well, the one thing I should point out is the fact that I have these 4s that I can deal with, but what do I know about the negative side? Well, there's nothing else in there. The only other thing that I have there is that the x goes to minus infinity is in fact minus infinity, right? Which means as I start here, which way do I have to go? Down. Does that make sense? Okay. What else do I know? Well, f of, I noticed that at 4, minus and plus, I have infinities, which means 4 is a vertical asymptote, right? What else do I know? The last bit of information is that x goes to infinity is equal to 3, which means 3 is a horizontal asymptote. And what else do I know? Well, I start at 2 over here, and the limit to 4 minus is minus infinity, which forces my graph to go down. And then I start at plus infinity, end up with 3, so I end up in that fashion. Does that make sense? Yeah? Yes?
How did you come up with the vertical asymptote?
Remember, by definition, the vertical asymptotes are where the limit as x goes to some fixed number are either plus or minus infinity. So since I have this one and I have this one, both of these will tell me that I have a vertical asymptote at 4. Yes?
I'm a little confused on the asymptotes x goes to 4 plus. Well, I meant x goes to 4 minus.
Okay.
I'm not. It seems like there should be something like after 3, like the line goes back up again.
Here?
Yeah, right there.
Well, going from the left, I end up with minus infinity, right? Going from the right, I end up with plus infinity. Think about 1 over x. They go in different directions. As it turns out, your function is not going to be defined at 4. That's actually the key idea about vertical asymptotes. Vertical asymptotes will always happen where your function is not actually defined. The number should not be in the domain. And so because of that, you're going to have a break in the graph. So it doesn't have to go back up because they're going to be separated. Does that make sense?
Yeah.
Okay. All right. Should we, let's do some problems. 13. We have the limit as x goes to minus 3 plus of x plus 2 divided by x plus 3. And so what is that limit? So what do we have to identify? And this is how we're going to solve these types of problems in a much more efficient way. Notice that if I put minus 3 in the denominator, I end up with 0, right? Now what do I have on top if I put minus 3 in? I have minus 3 plus 2, right? Which means I have minus 1. So one easy way of looking at things is the following. I know a number divided by 0 will either give me plus or minus infinity, depending on which side I'm coming off 0, right? So the way to work with these problems is the following. I'm going to have minus 1 divided by 0, but what type of a 0 do I have? Is it a 0 minus or is it a 0 plus? And the way you figure that out is the fact that minus 3 plus means I'm like minus 2.99, right? Plus 3 makes it a little over 0. And so that's going to be 0 plus, which means the whole thing is going to be minus infinity. Does this make sense? Do you understand what we're doing here? Yes?
We graph that?
No.
No.
We're not going to learn how to graph these for a while. To graph x plus 2 over x plus 3, let's see. I will have That would be the graph. Yes.
Can you re-explain the 0 plus part?
Yes. The key idea is the following. I'm looking at minus 3 plus. Okay? Minus 3 plus. You can view it, the best way you can view this is think about minus 2.9. Okay? So minus 2.9, and now if I look at x plus 3, that'll be basically minus 2.9 plus 3, which basically gives you 0.1, right? So now if you think about limits, you're basically going to get closer and closer to negative 3. So think about minus 2.99. Well, that'll just give you 0.01 and so forth, right? And so the idea is this is basically going to go to 0, but it's a 0 plus because I'm positive, right? There's no negative here. And so that's where the 0 plus comes into play. Remember how we identified the limit as x goes to 0 minus of 1 over x? The idea was we kept looking at it and we saw that the numbers were negative, but they were going closer and closer to 0. So we just called that minus infinity, right? Does that make sense? Remember? Because that was, in essence, 1 over 0 minus. Okay? Yes?
Just a quick, make sure. So the negative 3 plus, if that's a plus 3 minus, and you're coming from the negative side, but it's a positive number, so you're still going to be at 2.9. It's going to be positive 2.9, right?
Mm-hmm.
But whether you make it 0 plus or not depends on the bottom half of the equation, or whatever.
Yes. You're basically just looking for the sign of the bottom of the equation. You know it's going to be 0. And so the only question is it going to be a 0 minus, or is it going to be a 0 plus? And so that's why I said the best way to look at things is to actually just plug in a number that's obviously not necessarily as close as the number you want, but it's close enough. Like so, minus 2.9 is a good enough estimation of things. Now, this is where things get a little tricky, and this is probably too hard of a problem to start off with. Maybe. Let's start off. Let me ask you this. How about the limit? I don't know why I'm writing with whatever color this is. What would you call that? Pink? No. Is it pink? Maybe. Okay. Fuchsia. Huh? That's interesting. The limit as x goes to 1 minus of 1 over x minus 1. So the idea is the following. Today apparently I keep saying the idea is the following. Alright, we have 0, we have 1, we have 2, and so forth. 1 minus means I'm basically right here, right? Does that make sense? Which means 1 minus, think about it as being 0.9. Subtract 1 out of it, you end up with minus 0.1, right? Which means I'll have a 1 over a 0 minus. And so my answer will be minus infinity. Does that make sense? Everybody understands this? Yes.
If you have like a 1 plus, would that infinity be positive?
So if I look at the limit, as x goes to 1 plus of 1 over x minus 1, what am I going to have? Well, let's see. I'll use this fuchsia. X goes to 1 plus means I'm somewhere here, right? And so I'm going to consider 1.1. Something bigger than 1. It doesn't even have, if you want to be creative, you can use, 15 if you want. It doesn't really matter. The point is it's to the other side of 1, and the only thing we're interested in is what the sign of that particular expression is. And so now 1.1 minus 1 is 0.1, which is positive. So now I'm in a situation of 1 over 0 plus. And so I end up with plus infinity. Word of caution, this plus and this plus have nothing to do nothing in common. It doesn't matter which direction you're actually coming into. So now, let's look at a different example. Let's look at the limit as x goes to minus 2 minus of 1 over x plus 2. And this is why I said I probably started off with a harder example, because when that negative is there, things can get a little more confusing. So, especially for the beginning parts, if you want to actually think about the real line, where am I when I look at minus 2 minus? I'm to the left of negative 2, which means what I'm looking at is I'm looking at minus 2.1. Because of the minus, you're actually on the other side now, right? So minus 2.1 plus 2 gives me a minus 0.1. And so the limit will be minus infinity, right? Because I have 1 over 0 minus. Does that make sense? Okay. So, should I do the minus 2 plus as well, or do you see how this works? Okay. So, why don't we look at 15. The limit as x goes to 1 of 2 minus x divided by x minus 1 quantity squared. So what can we say about this situation? Sorry? Well, when you put 1 in for x, you get it. 1 minus 1, which is 0, right? 0 squared is 0. So you end up with 1 over 0. Sorry?
It does not exist. Because you're not going from a
Why can I say this? This is squared. It doesn't matter which direction I'm coming from, a quantity squared is always positive. So I will always end up with 0 plus. Sorry?
If it's 1 over 0 minus, it's also positive.
1 over 0 minus is minus infinity.
But did you say if it's x minus 1 squared?
Because of the square, yes, it doesn't matter if this is 0 minus, because when you square it, you'll end up with 0 plus.
Oh.
Remember the example I had in before with 1 over x squared? Right? It didn't matter which direction I'm coming from because it was squared, so actually it ended up shooting up anyway. Does that make sense? Everybody understands this?
But what if there wasn't a square?
Then it would be the situation of does not exist, because coming from the left would be minus infinity, coming from the right would be plus infinity. So in these types of situations, the one thing you have to keep in mind is you're always going to have a number divided by 0, right? The only thing you have to account for is the signs. So if the numerator is negative, the denominator is negative, then you end up with plus infinity, which was our situation before, right? Or was it not? I guess it wasn't. Okay. Is this making sense? So how about we do 17. It says the limit as x goes to minus pi over 2 minus of secant of x. So let's be a little more creative. So I don't want to write this again. So pretend like I wrote this to begin with. So 1 over cosine of x. Because now it looks in the form of 1 over 0, right? Well, one would assume that that's what you're seeing, right? Cosine of pi over 2 is 0, or minus pi over 2 is 0. Now the big question is cosine of minus pi over 2 minus positive or negative? So, what do? Right? This is a lovely, very accurate graph. Where are we at minus pi over 2? That's where we are at minus pi over 2, right? Minus pi over 2 minus will be somewhere here. Cosine is negative, right? Which means this will be 1 over 0 minus, so I end up with minus infinity. And again, let me just reiterate this. This minus has nothing to do with this minus or with that minus. Okay? Is everybody seeing this? If I would actually say minus 3 pi over 2 minus, if you look at the graph, I would actually be right there, which would actually make it plus infinity. Does that make sense? Okay. Did we have enough of these? Oh yeah, well we haven't gotten there yet. See, all I've done is here is basically deal with vertical asymptotes. I haven't gotten to the horizontal ones yet. So, so let's do 19. The limit as x goes to infinity of x cubed plus 5x divided by 2x cubed minus x squared plus 4. So, what should we do? Keep in mind we're going to infinity, right? So technically, first of all, let me take an aside out of curiosity here. What is the limit as x goes to infinity of x squared minus x? Positive infinity? Does everybody see that? Think about the fact that we're looking at a polynomial, and actually you were taught in pre-calculus to look at the behavior at infinity and minus infinity, and the idea was the only thing that really counted was the leading part. So whatever x squared does, that's what the whole thing will do. Right? If not, just think about the fact that x squared minus x is just a second degree equation. Either it looks like a u or it looks like an n. How do you determine if it's a u or an n? If the leading coefficient is positive or negative, right? So if it looks like a u, it will go to infinity as x goes to infinity, right? So the key idea to get from here is that the limits to infinity or minus infinity will always be determined, as far as the polynomials are concerned, will always be determined by the leading term. That being said, if I come over here and I put in infinity, I'll end up with infinity over infinity, which ends up not being 1. As one might actually be inclined to say. But what is actually it is equal to? So what we're going to do is we're going to do the following. The limit as x goes to infinity of x cubed multiplied by, so if I force out an x cubed on the numerator, what do I have left with? What am I left with? 1 plus 5 over x squared. Yes? Bless you. Yes? Divided by x cubed multiplied by, what do I have left? 2 minus 1 over x plus 4 over x cubed. Right? Everybody sees this? Yes? Okay. Now I can cross out the x cubes, and I'm left with the limit as x goes to infinity of 1 plus 5 over x squared divided by 2 minus 1 over x plus 4 over x cubed. And now you might ask yourselves, and this helps me, how? What is the limit of 1? 1. What is the limit of x, of 5 over x squared? 0, you say? Self-explanatory? So what is the limit of 5 over x squared? Well, if 1 over x squared goes to 0, multiplying that by 5 is not going to change my limit. Right? Everybody understands this? Okay. So if I come all the way down here, what do I get in the denominator? 2 minus 0 plus 0. Right? If you really want to keep the signs accurate. So what is my limit? 1/2. Is everybody seeing how this works? Yes? Okay. Wonderful. Let's see. 23, since you requested it.
So is that 1/2 of vertical asymptote or horizontal asymptote?
Yes. 23. The limit as x goes to infinity of the square root of 9x squared plus x minus 3x. By the way, later on we're going to discover something called L'Hopital's rule, and we're going to come back to it and talk a lot more about limits. There's a few types of undetermined forms, which means that you have to actually work out some things. First case you saw was a case in which we had infinity over infinity, and we don't necessarily know what that limit is going to be. A second case we're going to see is a case of this nature. If I put in infinity for x, I end up with 9 infinities squared plus infinity. Well, that's still infinity, right? The square root of infinity is still infinity, minus infinity. So I end up with infinity minus infinity. Now, because infinity is not an actual number, it's just saying that it's as large as you want it to be, infinity minus infinity could be anything. It could be 0, could be infinity, could be 1, could be 5, could be whatever number you can think of. Does that make sense? Okay, so then what do we do here? I erase the equal sign. Any thoughts what's coming? Square root of 9x squared plus x plus 3x divided by the square root of 9x squared plus x plus 3x. Multiplying by the conjugate. Kind of like a rule of thumb is if you see a square root, most of the times you actually end up multiplying by the conjugate, which is the permissible way of kind of getting rid of the square root, right? Because when you see square roots in general, you might think that you want to square them, but that's actually not what you can do. So now, what do we get in the numerator? 9x squared plus x minus 9x squared. Yes? What do we get in the denominator? The square root of 9x squared plus x plus 3x. Now 9x squared minus 9x squared is 0, right? So I end up with the limit as x goes to infinity of x divided by, so I don't have to rewrite this again. What can I do now? Well, as it turns out, I can do exactly what I've done in the previous problem. I can try and take out an x. How can I do that? I'll do it slowly so you actually see where things are coming from. So if I look inside the square root, if I factor out an x squared, I'm going to be left with 9 plus 1 over x plus 3x, right? Okay, this equals the limit as x goes to infinity of x divided by, if I take out the x squared out of the square root, what do I end up with? Absolute value of x, you'd say? What's the square root of 4? It's 2, right? Notice that when you take the square root of something, you end up with a positive number, right? And so we have to ensure that whatever we take out of the square root is actually positive.
Why is that again?
Because when you take the square root, you end up with positive numbers. If x is negative, then you can't take negative x, you can't take x out by itself. It has to be the absolute value. So then I'm left with the square root of 9 plus 1 over x plus 3x. Now, as it turns out, can we do anything about the absolute value? The answer is we can, because x goes to plus infinity. Well, if x goes to plus infinity, not only that it's positive, but it's actually quite very largely positive, right? We're talking about, 1,000, a million, a trillion, whatever the situation may be. And so, because we're going to the positive infinity, this actually ends up being the limit, as x goes to infinity, of x divided by x times the square root of 9 plus 1 over x plus 3x. Which equals the limit as x goes to infinity of x divided by, and now if I factor out an x, I'm going to be left with the square root of 9 plus 1 over x plus 3. The x's can cross out, and what am I left off as far as the limit? Yes? What is the limit as x goes to infinity of 1 over x? 0, so that doesn't play a role. So what am I left with? The square root of 9, which is 3 plus 3. So I end up with 1/6. Yes?
What happened to x and 1 over x?
Which x?
Like 9 plus 1 over x.
What is the limit as x goes to infinity of 1 over x?
So
That's a question.
So it's 1 over 0.
What is the limit as x goes to infinity of 1 over x?
0.
0, right? So that disappears. That's why we factor them out. Does that make sense? Yes? Now, just keep one thing in mind about this, because you might, I have a feeling you're probably thinking, why in the world am I going to bother with the absolute value if in fact I actually just have x? The only reason that's the case is because I'm going to positive infinity. If I were to ask you the limit as x goes to minus infinity, this will end up actually being minus x. Is everybody understanding this? Yes.
Okay, then why does the x disappear on 3x? It's 3 times infinity.
I'm factoring it out.
Oh.
And that's why I'm canceling it. I can't cross out the x here because I don't have a product. Yes?
It was x goes to negative infinity. How do you go from the absolute value to a
Well, again, the whole point is when you take stuff out of the absolute, the square roots, you want to make sure they're positive, right? So why would I get a minus x if I go to minus infinity? Well, because x is negative. So to make it positive, I have to look at minus x. Right? Remember, again, And again, when I said it in class, I know everybody said, yeah, whatever. It's not like I really have to remember it that much. But this is the definition of absolute value that says, if x is negative, I get minus x. So when I go to minus infinity, x is negative. So I end up with minus x for the absolute value. Does that make any sense? Yeah? Okay. Let's see. 5 minutes. What happens if I look at 27? Not 67. The limit as x goes to infinity of x minus the square of x. What would this limit be? Any thoughts? Positive infinity. Why positive infinity? And I'm not saying it's wrong. Well, square root of infinity is infinity. So I end up with this, again, the situation of infinity minus infinity.
Square root of infinity is less than infinity.
But see, that's not the way you need to think about things. That's what I was just saying before. Infinity is this general term. So you can't just say the fact that I'm taking the square root is going to make it smaller than some other one. Okay? Infinity is not a number, it's actually a concept. It's whatever imaginary, large number you can think of. Okay? So as it turns out, for this particular purpose, yes, infinity is going to be bigger than the square root of infinity because of the rule that I told you about polynomials and stuff, but it's not necessarily enough in general to look at that. However, what you can do is you can write it as x times 1 minus 1 over the square root of x. Why would this help? Well, because 1 over the square root of x is going to go to 0, right? Is everybody seeing this? Yeah. So if that goes to 0, then what you end up with is just infinity times 1 minus 0. So you end up with infinity times 1, which is infinity. Does that make sense? Yeah? So, having fun? Yes?
Oh, what about 34 where we need to find horizontal magic curves?
You only have to do up to 30.
We're not doing 34?
34 is graphing. You're supposed to graph it, and based on the graph, you're supposed to identify if it has vertical or horizontal asymptotes. And I find those examples to be relatively not helpful, considering as soon as we get to chapter 3, we're actually going to start graphing things of that nature by hand. So, okay, we have 3 minutes. I want to say a few words about. Do you want me to give you a cheat sheet?
Yes.
Yes, please.
What do you guess the limit as x goes to infinity of x squared plus x divided by x plus 1 to be? Positive infinity. What would you guess the limit as x goes to infinity of x plus 1 over x squared minus 5 to be? It'll be 0. What would you guess the limit as x goes to infinity of 2x squared minus x plus 5 divided by 3x squared plus 2 to be? I'll tell you, it's 2/3. Rational functions are very nice. Why? Think about, and this only works for rational functions. If it's not rational, don't bother working this, okay? But we're going to be dealing with so many rational functions that I figure this is an easy way to think about things. Think about this as being a polynomial divided by a polynomial. It's a race to infinity. Which one gets there first wins. Okay? The larger the degree, the faster it gets to infinity, right? That's the general idea, right? Because you have infinity cubed goes faster to infinity than if, or x cubed will go faster to infinity than x squared, because your numbers are going to be a lot higher, right? So you have a race. If the numerator has a larger degree than the denominator, it'll win out, right? Because it goes faster to infinity. So I'll have infinity winning out on top, so I end up with infinity. If the degree of the denominator is larger, this will win out. Well, I'll have a number divided by infinity that ends up being 0. Right? Last case, they have the same degree, so they'll basically fight each other. So what you're going to end up with is the ratio of their coefficient. Is this making sense? Again, this only works with rational functions. If you have any square roots anywhere, that's going to be different. Yes?
Do you have a quiz on Wednesday?
Yes. The quiz on Wednesday is basically chapter 1. And, okay. Maybe I guess I'll spend 5 minutes on Wednesday and write this out in a rigorous proof way instead of just saying it in words. So you actually have it written out. I'll use like P's and Q's and stuff like that. But anyway, for now I guess you understood what's going on.